Okay, so we'll be looking at future dimensionality reduction and a feature selection. So this one advanced now, so we're going further.
All right.
Right. So our lesson objective at the end of this presentation, we'll understand what dimensionality reduction means and why it is important. Then, okay, all right, sir, can we just pause for 2 minutes, sir? So, like I said, we'll be looking at what is dimensionality reduction? Why is it important? Then what is the cause of dimensionality? When you mean the cause, what are the stigmas and the implication of that cause on dimensionality? Then when do you compress your features? Then you want to know how PCA, LDA, and SVD works. Then we'll now talk about advanced feature selection methods like RFE, Boruta, and SHARP. So there are other feature selection methods, but I'll be talking about these ones. In intermediate class, they will be looking at things like ANOVA, chi-square, and yeah. So, but you and I will be looking at RFE, Boruta, and SHARP value.
Okay.
All right, sir.
Which one is the Sarima and the rest? Is it under intermediate or advanced?
I didn't get it, sir. Which one is what?
Sarima. Is it under intermediate or advanced?
That's advanced also. Okay. Yes. So I'll be looking at maybe what I'll do is for your next class, I'll just bring it in so that we'll talk about it also.
All right.
I had to divide this class into two so that it won't be too much, because I realized that intermediates, they were complaining. The last class we had, it was almost 70 slides.
Wow.
Yes, sir. Even this one is close to 100, so I just divided into two.
Okay, sir.
Yeah, so that it won't be too much information in one slide. Yes, sir. All right, sir. Okay. All right. So introduction to dimensionality reduction, as you have said. So this is what we are just talking about, dimensionality reduction. If you look at from your left, the cube, you can see the data.
Yes.
How the data is exactly. It's passed into what? 4 different. So you can tell that these are 4 different types of data. So you can see duly represented, the yellow, the green. Then you see that from here now, the dimension is what? Is being sparse. This is sparse. So when you bring from 3D, you can see the way it sits on 3D and to what? Onto 2D. But this is what we want to achieve, sir. We are talking of dimension. And why are we doing that? You will know as we go on. This is what we always want to achieve. When all your features are aligned, there's always a very easier way for you to carry out your classification or whatever kind of model you want to build. So it's always very easy. So it starts like this. We convert and we reduce. So that's what we'll be looking at. So what is dimensionality reduction? I said that is the process of reducing the number of input variables, that is your features, in a data set, while retaining as much relevant information as possible. Yes, sir. Because when you realize that there's a problem we always have is that sometimes they give you some data sets and there are a lot of features that are not necessary, sir. Thank you very much, sir. A lot of features that are not necessary. In fact, they don't have any effect on anything on what's it called, on that particular maybe case study. Exactly, that's what the case study. So what's the motivation?
In fact,
okay, go on,
sir. During the last training, I think I was telling Mr. Blessing why we built the diabetes model using I think we use flaps there. Yes. I was telling him that as a doctor, that the future, the aspect of the future that has to do with the skin sugar, shouldn't even be represented in the future, because as a doctor, we actually don't, although we just look at it physically when a patient presents, we look at the skin to check for dehydration. I told you that it's not really a major feature that should be in that something. Yes.
I think I'm happy that you are saying this, because I was just about to say the same thing to tell you that from DSA we learned a lot of things. For someone like me now, I had to go and befriend a radiologist. In fact, there are 3 of them. because I realized that most of the times these data scientists we are building model for health people. The people that will use it, we are not carrying them along. Just like what you have said, you saw some features that are not relevant to what for classification or for whatever detection we are doing. So, Mr. Are you still here, sir? Oh, let me pause. Network.
I did like 20 seconds.
Okay, can you hear me now? Is it better, sir? Hello, Dr. Bello, can you hear me?
Hello?
Can you hear me
I
now?
said I didn't hear you for like 30
seconds.
Yes, I can hear you now, sir.
You can hear me now. Okay.
Yes, loud and clear.
Okay,
I didn't hear you for like 30 seconds.
30 seconds. Okay, I said I wanted to also mention what you said now. And I said it has pushed some of us realize that as data scientists, we are creating models that are not usable, sir. Especially in the health sector. So what I did was I had to befriend 3 radiologists. There are about 3 of them now. Dr. Afolabi of UCH, Dr. Fatade. Because when I met them, I realized that there were some features that were adding, sir, that are not necessary, sir.
Necessary, yes, sir.
Yes, we are just concerned about performance, and he was telling me. In fact, there's a work I did together with Dr. Fatade, and we won an award. Our accuracy was the lowest in everybody's work, sir. But he was telling me that what you guys look out for, sir, is specificity and sensitivity.
Yes, sir. Yes, sir.
I even as a tutor, I just knew that. So I realized that it's not enough for us to teach data science, and we're working on air data without having input of medics amongst our work.
Yes, sir.
So now that I know now that you just told me now, my next paper that I'm writing, an experiment I'm doing, I will share with you.
All right, sir.
Yes, I will share with you.
Yes, sir.
So that you'll be able to give me insight. I will share with you, sir. So we don't mind. If you want us to publish your name, we'll put your name there. But I will share because I realized that we won award as our accuracy was 81%. But our model was
still good.
Yes, sir.
81% is also still good.
Yes, but he told me, but the sensitivity and the specificity, he said they were wonderful. Yeah, because people were coming and presenting 97, I was scared. He told me, he says, no. He said, this is an health app. We're trying to do a severity level of sickle cell anemia using a microscopic blood smear.
Oh, okay, sir.
So I created an algorithm that will measure the sickle cell through elongation. Exactly. So now so we now divided into mild, moderate, and severe. Yes, sir.
Yes.
So our sensitivity was about 90 something and specificity also. So he said that's what you guys are looking at. How sensitive is the model to pick the right diagnosis?
Right, yes.
And how specific is the model?
Yes, sir.
So if you have like 100 cases, did he pick 95 out of them, or he pick only 50 or 40? 50. Yes. So I learned something. Right, I learned something new. So I'm happy you have said this, sir. So this is a very good one. So we want to simplify our models. We want to reduce overfitting. That's why we find out that people have models. They say my model is 99% accuracy. It's a lie, sir. If you test against other matrices, you will realize that model is what? That model is what? Is overfitting, sir.
Overfitting.
Yes, the model is overfitting because they are put really irrelevant. So the model is just overlearning and is not actually giving the right insights that we need. Yes. So they want to improve computational time. You realize that when you are talking to Mr. Moe, for people that did that project, somebody told me, say I was running program from 9 a.m. It did not finish till 2 p.m. It's things like this, sir. Computational time. You did not remove irrelevant. So you can see, he left irrelevant. You are just training the system based on all data sets. So there's no, then if you notice people that use data set that were too much, their visualization was never fine.
Yes, sir.
You
Yes,
how
sir.
can you, sir,
In
want
fact,
to
I told some of my squad members that as much as possible, most
yes,
of them were looking at creating a model. I said the best way to do is to start with a very simple model.
thank
I
you.
was seeing some people talking about 2,000, 5,000 data. I said, for
Ah,
what? Let's
yours,
start with a
maybe you said
simplicity.
5,000. There was one I saw that the person used 100,000.
Ah,
Yes, if I
wow.
find it, I will screenshot and send you. He now did a correlation graph. So you cannot read anything on the correlation graph because when
I told some,
you're
I
having
said,
100,000 with features of about 38. How do you want to represent the
yeah.
correlations, sir? So,
Yes, sir.
so those are the things. So those are the things. You are very, very right. I'm really happy. I learned this in after DSA. One of our paper was rejected and I was so bitter because I spent months on it. So somebody advised me, say, go and befriend medics. Start
Yes,
to
sir.
talk to
Yes, sir.
them. I started talking
Yes, sir.
and I realized that they have a lot of blunder in the work that we have been doing, sir.
Yes, sir.
No wonder
Yes,
a
sir.
lot of models have been built, sir. They are not useful for anybody because the people that will use them were not carried
I
along
not.
during the
Oh, yes, sir.
process. Yes, they were not
Yes.
carried along. All right. So thank you very much,
Yes,
sir.
sir.
Yes, sir.
You're welcome.
Okay. So we look at it. I just said reduce overfitting. Too many features can make a model fit noise instead of signal, just like what you have said. So
Yes, sir.
the fewer the future, the simpler and the more generalizable words the model will be.
Model.
Yes, the model will be like what you said, start small. Why are you building
Yes, sir.
with 5,000 data sets?
Yes, sir.
Look at my pneumonia model I want to do now. I have about 132 DICOM data sets. And my supervisor was like,
Okay.
it will not work. Then Dr. Fadane said, it will work. He said, all we need to do is that we make sure that the data is well annotated and labeled. He said 100 and 200 data sets will work for what you want to do. Because what we are trying to do is that we are trying to do first classify for under 5. We want to first classify for under 5. I think I'm going to, let me change networks as well you can hear me.
5 years.
Hold on, sir. Let me switch to the second.
Okay, sir.
Let me switch to the second network so you can hear me better. So he was saying that we are looking for sickle cell pneumonia amongst 0 under 5. That's 0 to 4.
5.
Yeah, 0 to 5, sir. So what we are trying to do a multi-stage model. So the first thing is that the model first separates pneumonia data set from non-pneumonia.
Yeah.
It was talking to them that I realized that there's a difference between pneumonia data set, non-pneumonia data set, and normal data sets. I thought, can you hear me now, sir? Okay. Mr. Bello, I'm back. Can you hear me? Like I was saying, I said in the process of talking to a medic and the radiologists that are working with me, I realized that there's a difference between pneumonia data, non-pneumonia and normal.
Yes, sir.
He said there are 3 different things, and we have been thinking it's just pneumonia, and when you say non-pneumonia, it is normal. He said no. He said it can be non-pneumonia, but there are some other things also that are still embedded in that. Exactly. Yes. So those are the things. So you can improve computational time. He said high dimensional data requires more memory and processing. And if you do that, you'll be able to reduce your training time for algorithm. So it's a lot of things that we need to put in space. So as I was saying, we are trying to do what we call for the pneumonia data. First, classify the pneumonia and non-pneumonia. Then secondly, do what we call localization. Yes, sir. At what region is the pneumonia located in the body of the patient?
Body.
He said there's either there's the lower right region or the lower left region or the
upper lung zone, middle and lower lung zone.
Exactly, sir. Upper, middle, and lower. Yes, sir. Yes, sir. So that's what we want to do. Then we'll convert into an app. Yes.
Well done, sir.
Yeah, thank you very much, sir. All right. So these are the things. These are things we are familiar with. So we've spoken about them. Then the other one I've not spoken about is that it removes redundancy, and we spoke about correlation. Many features may carry similar information. So why are we repeating the same thing? Then noise reduction. Then you can interpret features very well. Say sometimes reducing features reveals underlying patterns. Yes, you are right, sir. You will see some things that are very, very, you will not realize that those ones you are dwelling it on don't even have any effects on what you want to do. Yes. Then undo cause of what? Of dimensionality. As dimension increases, data sparsity increases, and it is harder to model. Yes. The larger the dimension, very difficult to what? To model. So what is the cause of dimensionality? Just like what I've explained here, say as the number of a feature increases, the volume of space increases exponentially, making data points sparse and harder for algorithms to generalize. And the consequences is always overfitting, sir. I've seen a lot of work that people have done, sir. When I see the work, even me myself now, I myself, I just get I just laugh and look at it and know this model, you say your model, you got 99% accuracy, 99% precision, 99% F1 score, 99% AU. I was asking one guy, he said, yes, now we did good pre-processing. I said, no, sir, there's something wrong. A model cannot be 99%. Which data did you use? But when I say such things, people get upset with me. So I'm very careful when I talk about things like that. Yes. Then what they don't know is that the model is performing poorly. Because if they bring a data set from you now that as a doctor, and you have removed what's it called? And you have removed all those unnecessary features. By the time you put it in this model, sir, this model will underperform.
Yes, sir.
They will not ask him, come, sir. You did something, you say 99%. Now we have given you clean data by Medic. Well clean. Your model is giving us 59%. What happened?
100%.
Because from the beginning, the model did not generalize. The data they were using was what? Was just too sparse. So look at it. Like I said, you can see what happened. Can you see? Look at it. See the way the data is. Can you see? The division of decision boundary. This is the decision boundary, but because of sparseness, the data is just one place. So the system will only work here, sir, and forget these other places because he can't see them. He thinks this is a cluster. And sir, how can you make a decision, sir, based on only these features where there are other features? Thank you very much. Other features. Look at the correct one now, you can see. They are closer to, you can see they are not. So you can look around and see what's happening. Why is this feature on this side? Why did they intercross? You get that kind of something, sir? It's easier. Look at this one, it's underfit. It will only come and pick only one feature here. Look at it, or come to pick the extreme because it is not. So that's the problem that we have with our models, and that's the reason why we are advocating now, because I'm a member of AI ethics in Nigeria. So we have started advocating that for anything that has to do with medical AI, in your team, you must have a medic. Yes, you must have somebody who knows that area you are working on, sir. Not just anybody. All right. So what is the context? Just like we have said, you can see now, 2 features, sir. 100 samples. You can see for 2 features. Very easy, as you have said, sir.
Yes, sir.
But look at, sir, when you now want to work, you say 100 features, 1 million samples.
No
so there's
samples.
So you see that there's problem.
Yes, sir.
If you create a model with 2 features and 100 samples, sir, your model will work better than anybody that used this 10 and 100.
Yes, sir.
How do you want to generalize 100 features, sir? It's very, very, it's very unrealistic.
Yes, sir.
Very unrealistic. So more features, exponentially more data is needed. 200 samples are fantastic.
Yes, sir.
And that's why when we get into deep learning, I enjoy deep learning. Images. You can train a model on 10 images, sir, and it will still perform better than a machine learning that was trained on what? On 500,000 records.
100,000.
Yes. As long as it has been anonymized and well labeled, it's working fantastic, sir. So that's just to show the context of the course of a dimensionality. Yes, sir. Yes, sir. All right. So what is feature compression? Because when we have issue of dimensionality, the cost, we must look for how we can compress features. So feature compression is the process of reducing the number of features. Or you call them variables in your data set. Yes, sir. But you are making sure that you are retaining the most important information. Yes, because now I have a data set that is for pneumonia, a numerical data set. The first thing I need to do is that I need to call you or call Dr. Fatadi and send you.
Yeah.
You will not tell me which of these features is the one that I need to use to train my model.
Yes.
Exactly. So that's what is called the principal component. When we are talking about principal components, it looks at it, it transforms original features into fewer and often uncorrelated. So that if you have too many correlated features, they are all doing the same thing.
Yes, sir.
In fact, tonight after a class, I have the data they sent to me. I'm going to send to you, sir. Please, sir. You help me look at it.
Yes,
it's for tuberculosis.
All right, sir.
I really need your input. So you help us tell us which one of those what's it called? The
features
that we need. So I won't waste our time. Yes. Then you can see it simplify the data set without losing critical information. Yes. It's as simple as that. All right. So you can see, look at all these features they put in.
Yes.
Was all this, but it has gone lower dimensionality. You can see it takes it into two features. It looks at all correlated one, compile them into one feature, and use only uncorrelated, so that when you are decoding, the system already knows, model knows, so decoding will be easy. Then it reconstructs the feature. So you can see the features comes out and the model performs fantastic. So you input your feature, it encodes it, reduces the dimensionality, then decodes it to the network so that you can understand that what we have done is that all correlated have been compiled into one feature, uncorrelated have been left to breed on their own. It's as simple as that, sir. And you see that your model works, and that's why you find out that if you go and check journals like Web of Science, Nature, you hardly see any white man, sir, and you see 97% accuracy in any of their work. You hardly will see 97% or something in their work. So are you still with me?
I'm with you, sir.
Okay, great. So you always see the highest I've seen their work is 81. 81. Because the work has been properly done. Features have been properly compressed to make sense. Yes, to make sense to the model. So the model is not overperforming and it's not underperforming. Yes, sir. All right. So why is it needed? Like we said, we reduce overfitting. Why do we need? Yes, too many features may fit noise instead of true patterns. These are things that you and I have discussed also. So these are just repetition just to make sure that, you can see. So I said simplify visualization. You can compress 2 to 3 dimensional, which allows plotting of data for, you compress them together. There are lots of features that correlate, compress them as one and give them a new feature name.
Yes.
So it's as good as that. Then we can mitigate. When we can do feature compression, then we can mitigate against the cost of what? Of dimensionality. Yes, sir. You can. Very easy. You are good to go. Right. So when and when not to use it, when to use feature compression and when not to use feature compression. So we'll start from the left. When you have many correlated variables, like we know already, we must use what feature compression. When your model is suffering from overfitting, yes, the model is overfitting. You say your model is 99%. They bring data from external data set. Your model is not performing well. It's saying 49% accuracy. Then you know that what the model you have created is what is overfitting. Then when training is computationally expensive, yes. Look at me, I and my friend now. We are working on segmentation. We had to write a code that can segment what do you call this thing from brain? They call it, is it Giroma or what do you call them? From the brain, the white matter from the brain anyway. Let me just, as I know, we divided it into 4. We realize that if you see what has happened, we have spent close to like in this week now, we have spent almost about 50,000 around data because we want to use GPU. So you can see that training is what? Training is expensive.
Hello, sir.
All right. Sorry, sir. It's
okay, sir.
It's been a tug of war with us here since Monday.
The network.
I'm telling you, sir, since Monday, it has not been. Doesn't be funny. I was telling somebody, I say, I hope MTN is not leaving Nigeria. Because it's becoming very, very scary. We can hardly, you can't even use the network without having issues on it. So we're talking about, you and I were talking about when to use this. And I was citing something that is going on. I and a colleague of mine, we are trying to extract hippocampus from brain matter. So we are writing yes, sir. Yes, sir. So we first extracted the brain from the skull using FSL. Then now we are now trying to segment the right and left hippocampus from it. Training is very, yes, sir, very, 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 very computationally expensive, sir. We spent nothing less than 50,000 naira on data set for this week. Because we don't have GPU, so we have to go and rent a GPU user. So you can see. Then when visualization of pattern is difficult, how can you look at, sir, how do you visualize 1 million data sets, sir? 1 million. It's true now. You can't represent it on graphs, sir. I'm happy you're laughing, sir.
Yes, sir.
How do you represent it on a graph, sir, on a pie chart, on a bar chart? Even if you use a scatter plot, sir, it won't make sense.
It will scatter.
Yes, sir. It will just scatter everywhere, sir. It won't make sense. So that's just that's just it. Then when not to use compression, when you want to watch, when feature interpretability is crucial. Exactly. Maybe we want to for medical diagnosis and finance, things like that. We need some features that are necessary. And that place, it works when you want to do maybe your EDA, exploratory data analysis. Yeah, exactly. But not for you building your model. Then when you need to explain predictions using original variables. These are the things I'm going to teach you. That's why I was telling them in intermediate class. I said, I was teaching them something. I told them, I said, what I do is that even when I want to carry out anything on a particular data set, always make sure that you have created copies of the data set. So keep your version 1. Then when you are creating or you are compressing, if you do feature compression, name that new one and call it compressed feature files. Exactly. And save. So that you will know that this is the original, this is the compressed. So later, if somebody is asking you to say, come and explain your prediction, you say you compressed. Where's the normal data? When they look at it clinically and with what you have done, then they can correlate that, there's a correlation between what you've done, but you needed to do a bit of compression to make sure that your model can work very, very well. then you don't need to compress a data set that is already low dimensionally. Just like that one that we have 2 features now. What are we compressing in 2 features? Some people just want to, some people think that's why we learned recently when we went for that ethical course I told you. I think because we are data scientists, we want our work to do fine. We just do some things that are not necessary, sir. They are not necessary. The guy that taught us is a white guy, sir. He doesn't even have BSc, sir. This is a data science technician. He works as a lab technician. What do you call them? A computer lab technician, sir.
Yeah, yes, sir.
But the things we learned from him, I wondered, I said, wow, we've been doing things wrongly. Especially when it comes to medical data sets. Yes, sir. A lot of things we have been doing wrongly. So we now know when to use what? Feature compression and when not to use it.
In fact, that is what prompts my interest in AI/ML, because I have seen some mention, and personally, I believe that some things are wrong, and the best way to correct things in that field is just to be part of it.
Great.
That was the drive.
I'm happy, sir. I like you. I think that's why you and I will become friends, like I became friends with Dr. Fatadi. The same thing he told me. He said, I'm not fighting you guys. I'm not, you guys, I can't do what you guys can do very well. But if I don't come into the field, I won't be able to talk to you people.
Yes, sir.
So when I write my codes and do some things, he will tell me, put comments everywhere. I send to him. He will say, Mr. Olajide, this one is not necessary. We don't need it. Remove it. So before we got to that stage, I will get upset and say, I did not sleep. You say, you'll have told me before you were to do. So now, before I do anything now, I send the data set to him. I say, give me, what can we get from this data set that they have given to us? What can be done with the data set? Because a lot of people just sit up and say, diagnosis. I suddenly realized that some data sets are not good for diagnosis, sir.
Yes, sir.
They are just good for classification.
Location.
Some are just good for correlation.
Sure. Yes, sir.
So, and we don't know. We will just carry everything, build model, diagnose this thing, diagnose this, and say, no, it's not all data sets that you can use. He says some are just to draw insight.
Yes, sir.
So it's good, sir. I'm really happy. I'm impressed that you are joining our, and so we'll be able to, now that I know, sir, I've stored your number already before. So I'll put it part of the list of my medicines. If I have issues, I'll just call you and say, sir, we are doing this. So what do you think?
Yes, sir.
Thank you so much, sir. I really appreciate it, sir.
Yes, sir.
Yes, sir. So let's look at common dimensionality reduction techniques that we have. All right. So these are the ones that we have. We have the PCA, the LDA, and the SVT. They are all linear. But the only one which is supervised among them is the LDA. Can they preserve variance? Yes. But LDA seems to be able to maximize class. It does very well. Yes, LDA does very, very well. In fact, you can use it in all situations. So let's go to them proper. I just did a table so that all these things just, so that your brain can pick it back later. Oh, somebody is even asking, you have learned something, what did you learn? So all these tables just help you to be able to differentiate in what they are doing. So let's start with PCA, Principal Component Analysis. What is Principal Component Analysis? I said it's a dimensionality reduction technique that transforms a data set with possibly correlated features into a set of linearly uncorrelated variables called what? Principal components. That's what I was explaining to you that time. I have like 100 data sets. The 100 data set has 30 features. Out of the 30 features, sir, 16 out of them are the same thing, sir. So what do? We create a group for them, sir, so that they become what? Linearly unrelated. So out of the 16, we say, okay, match 3 together. Okay, these 3, if they join together, they give us a new component. So we keep them. This other 3 gives us a new component. So before you know, sir, you'll have created what you call principal components. Like suddenly I realized that there are some diagnostics that you want to do, sir. You cannot expunge age from it.
Yes, sir.
I didn't know before.
Yes. Age
I
is a
did not
very crucial factor.
I did not know before, sir. I
Yes, sir.
had to send letter and retract my journal, and I'm rewriting it now. You cannot expunge gender from some things you want to do, sir.
Yes, sir. Even ethnicity.
What did you say, sir?
Even ethnicity.
Ethnicity. Thank you very much, sir.
Yes. Yes,
Thank
sir.
you very much, sir. So a lot of things like that. So they are called principal components. So you must make sure. So when you now see somebody who says ethnicity, they now say black. Then black, you see again says region, Africa. Africa is black already, sir. So why are we having a duplication of? I hope you get what I'm saying, sir.
Yes. Let me share this with you, sir.
Okay, go on, sir.
A friend of mine had a patient.
Okay, sir.
And while the friend was treating that patient for a very long time, the patient was not improving. So I said, okay, what have you been giving this patient?
Yes, sir.
Then he told me the list of what he has been giving. I looked at it. I said, all these things you've been giving, it's very okay. Then I said, let me just ask him. I said, okay, from which country is the patient?
Yes, sir.
He said India. He said India. Immediately he said India. I said, oh, now I see the problem because we don't give Indian patients ciprotab. It causes dehydration for them.
Wow, wow, wow.
So I now told you that ciprotab is the problem in this your treatment list. You have to remove it. And immediately after that, he discharged the patient the second day.
Can you imagine, sir? So that's a very principal component.
Yes, sir. Yes, sir.
And you need to teach your model to understand that in diagnosis, that if it's creating a model to diagnose this side of people from this region, like India, you must. Sir. Can you see? Can you see? Yes, this is good. This is good. This is good. Thank you very so much, sir. I'm glad that this is on recording, so that this is good. This is good. This is good. Sir. All right, sir. Let's go on, sir. All right. Look at principal component analysis that we call PCA. What is our goal? We want to find a new set of orthogonal axes, which we call the principal components, that capture the maximum variance in a data set. Yes. Does it relate? Does it represent exactly? That's the word. When we say maximum variance, those variables that represents the whole culture of the data set. Yes. And that's it. And what are those steps that we take when we want to do PCA? You remember standardization, sir?
Yes, sir. Standardize the data.
Do you remember standardization that we did during our DSA?
Yes, yes, sir.
Exactly. So you ensure that all your features are contributing equally. So it's either we reduce to 0 and 1, or we use the mean and standard deviation.
Deviation.
Exactly. Yes, exactly, sir. Then we can compute what you call the covariance matrix. There's something called covariance matrix. These are things we'll be seeing in our practical. So it captures relationship between features. Yes, you use it. We call it feature importance model. You can build a feature importance model. So what is the relationship you want to know between age and time of diagnosis? Is there a correlation? Exactly. Within age and a response to treatment, is there a relationship? Exactly, sir. Then you can calculate your eigenvalues, or call the eigenvectors. What does it do? It helps you to define new axes. Yeah, it creates new principal components for you. And it tells you, okay, the variance here is good. You can use this feature to carry out your diagnostics. Okay. Then you can project your data on top of a K component, which is called the K dimensionality. Okay. So there are lots of models under this PCA. So we'll be looking at KNN, which is your K nearest neighbor.
Neighbor.
Yes, sir. So you can use that also to reduce dimensionality, but you will never lose the most information. You won't lose the relevant information. Okay. Yes, so this is just the mathematical expression. Like I told those in beginners class and what's it called? Our intermediate class. I said everything that we are doing in data science was either gotten from what? Mathematics, statistics, physics. So those are things we are just borrowing what? Borrowing their this thing. So this one is just for your own consumption. It's just for consumption. So if somebody is saying, oh, you are talking about principal component, eigenvector. What do you know? You just there's a mathematical what? There's a mathematical formula for that, which is x is equal to t p raised to power t. Exactly. Where your t is the score of your matrix, the whole principal component. Then P is the loading matrix, the new axis that has been created. So raised to power what again? Your score of your matrix. So you can see it like that. So that's just as variance is explained by each component, which is proportional to what? Its eigenvalue. So what exactly is it proportionate? We look at age to what? Age to time of diagnosis, or age to response to diagnosis, or to response to treatment and things like that. So it just stands side by side. So if I'm going to express it here, that's one of the good things about Python. That mathematical distance that you and I were looking at, and is looking very scary.
Yes.
We can use a Python code to do that, sir. So all we need to do is what? I told you, I said there's no library that you cannot find in your scikit-learn. I think I was telling you in our live practical.
Yes.
I told you.
Yes, sir.
Just know the name of the library. If you don't know, go and use your help in your Python. Python will tell you libraries. It will bring out all libraries. You can take a whole day to read the libraries that you need. So if you call our scikit-learn decomposition, anytime you hear the word decomposition, we are talking about feature compression. Exactly. We want to undo dimensionality. So you see that we called what? We call the PCA. Exactly. Then we talk about standardization. We also called what? A standard scalar. So from there, what we have done here is that what we have done in this coding here is that if we first do our transformation and standardize, and it's still not giving us the kind of correlation that we need, then we can also infuse what? PCA into it. But for every time you get your data set, the first rule of pre-processing is that what? You must first standardize. First standardize your features. If you now plot and realize that no, they are not yet standardized, then you can now apply PCA to it. So you can see, so that it makes it fit. Then you can now print and so you show us now the variance ratio. Let's see what is happening in that place. Is it now well compressed, and is the dimensionality what? Is it now proper for a model to be able to what? To be used on it. So that's what we do. All right, then you can visualize. I just put PCA component visualization. Yes, you want to visualize and see what you have done. So you can see, you can create a label for it. So it's just as simple as when you start doing these things, you'll see them in action. So, but so far, sir, I hope I'm carrying you along, sir.
Very well, sir.
All right, thank God. All right, so let's go on there. Then we now talk about the LDA. It's called your linear discriminant analysis. What does LDA do? It's a supervised. Can you see now? That is the only one that has to be supervised. Others are unsupervised. Your SVD and your PCA are unsupervised, but this you have to supervise it. It's a supervised dimensionality reduction and classification technique that finds a linear combination of features that best separates two or more classes. Exactly. So it looks for a linear combination of features. It joins together and say, okay, if I have age, can I create age group out of it? Yeah. Instead of having, there are sometimes you have 10,000 data set and there's age, and the age that you need, maybe there are different ages. And the age that you need in that data set is from the age of 18 to 45.
Yes, sir.
So why not create an age group so that it will knock out all those people that are not in the age group? You get what I'm saying, sir? Maybe you have from age 0 to 78. And what you need for your diagnosis is from age 18 to 45. So you can create a new age group. So it separates two or more classes. So now you're taking it out. I don't need all this I need what? I need the whole class of what? 18 to 45. Then you cannot say, okay, 18 to 25, 26 to 35, then 30, 36 and above. Then you already have four what? Classes. Then those 4 classes will now come with their features that follows them. Then all other ones you discard because you don't need them for your what? For your model. Yes. So why did I say supervised? It uses label to guide what? Feature projection. Yes. You must tell it what you want it to what you want it to what you want it to compress. So that's why we call this supervised. Supervised learning. You know, under machine learning, we have supervised learning and unsupervised learning.
Yes, sir. Labeled
and unlabeled, exactly, sir. Yes. So what is the goal? We want to maximize the ratio of between class variance to what? Within the class variance. Just like I've said, age and age group. Between the class variance and what? Within the class variance. So output, new axis, which is called what? A discriminant component that best separate the class. So you know that the output of age and age group will be different, sir.
Yes, sir.
Exactly. And this is much more applicable when we are doing things like pattern recognition, medical diagnosis, and classification. Yes. I use LDA anytime I'm working on especially with the last one I did, the blood data set that I did. Especially when you're working on images, it's also good for your numerical, but when you're doing images also, you can employ LDA. Yeah. Then this is the formula for LDA. So LDA finds a projection matrix W, which maximizes what? You can see that J into W. So you can see there. So that's just it. You remember our T there now when we're talking about our T. So it uses the same it picks the weight of the principal component. So it takes it with between the class scatter matrix and within. So that's just as simple as that. Please don't let the mathematical expression disturb you because we have it in Python. We are into Python. Can you see our LD? Can you see this long side? Just imagine telling somebody to use this formula and look at what we will need to do. We just say scikit-learn dot discriminant analysis. Then what? We import what? Linear discriminant analysis as LDA. Can you see, sir? We put our NDA into the data set and we tell it to what? To print it and explain. Let's see what the ratio of what? Of those are components. Can you see that we have specified the components, sir?
Yes, sir.
Components, depending on how many components you want to what? You want to separate. It can be more than 2. If you remember, I said here what? I said between what? 2 or more what? Classes.
Yes, sir.
So it can be between 2 or more classes. So what is the comparison? I love to do this anytime we do it because PC and LDA almost have the same, they are so close, but they have some differences between them. When it comes to the issue of supervision, PCA is unsupervised. You don't need to tell you what to do. But we know that LDA needs what? Supervision. Exactly. Then what's the objective? We want to maximize variance in PCA. Yes. But here we want to maximize class separatability. What's the difference between age and age group?
Yes, sir.
Then what is our output? This one gives us principal components. The other one gives us what? Discriminant components. Then what's the use case? PCA is good for data compression. LDA is good for data classification, sir. So we now classify data of similar features together, sir. So if you now have maybe like 20 features, we'll not compress it and classify it together. Okay, these ones are correlated together. They are the same thing. From 20 features, it becomes 5, or let's say 7. So that's what we do in LDA. As PCA is for data compression, LDA is for what? Data classification. Yes, sir. Then going on to the last guy now, which we call the singular value decomposition. Exactly. It's called SVD. I said it's a matrix factorization technique that decomposes any rectangular matrix into 3 matrices. Can you see? It breaks down a data set. You can represent your data in a matrix and see what it looks like, sir. So when you now split that matrix, that singular matrix of your data into what? And it's the only reason why you can do that is what is when your metric shape is in a rectangular form.
Okay.
Rectangular form can be, it can look like from up to down or from left to right.
Right.
But if it's giving you a perfect square, sir, you don't need to do any decomposition.
Okay.
Immediate length is more than breadth, or breadth is more than length, sir. Then you know that what you can use what you call your singular value composition. Exactly. So what do we do? What's the purpose? It reduces the dimensionality of data. It's also presenting what is preserving as much information as possible. Exactly. Then it captures latent structure in data. That's one good thing about this one. When your data is too much, you can use it to capture what latent structure. How does even this data look like? And when I was talking to them yesterday in class, that'll be 2 days ago, and we're talking about extremities in data extremities. Is it that to the right extreme of the right, or what to the extreme of the left? So we are talking about that. So when we're talking about handling what very high dimensional, so when you see a data that has very high dimensional, like that first diagram I showed you, the 2D, you could see the way the dimension of the data was. Instead of trying to bring in LDA or PCA, just use SVD. It will bring all the sparse matrices together, all outliers. It will compress them together at once. So I said, what is you see now? Latent semantic analysis. Basically, we use it mostly when we are building what? Natural language processing models. This is like a kind of technique that is used for ChatGPT. So that ChatGPT will not be hallucinating.
Yes.
If you notice that some months ago, when you ask ChatGPT some question, it will be telling you something that is not there. But if you try using ChatGPT now, you realize that ChatGPT is getting better.
Is that the major purpose of the introduction of RAG? That hallucination aspect.
Exactly. Can you see? Because, sir, there will be hallucinations, sir, when data has not been what are the principal components of the data that you want it?
Data.
Thank you very much. It will hallucinate, sir. It will decide on its own and say, okay, since I've seen this before, whereas it's not correlating. So because it has been created to generate response, it just generates response for you. And if you're not careful and don't verify that response, sir, it will give problems, sir. Look at it. They are using what? Recommender systems. You need just like building a system now that tell you if you put like 5 symptoms and recommends that you need to see the doctor or you need to go and take a particular. Sir, if we don't do the right things, sir, it will give people wrong diagnosis, and if you are not careful, people will go to jail.
Of course. Yes, sir.
And there will be loss of life. So one has to be what?
I think that is the aspect of the ethics you were talking about.
Thank you very much, sir. Thank you very much, sir. It takes a lot of, so all this have to be put in place. Not all information are useful, sir. Your model must be able to understand that some features that has come in is not pertaining to anything, sir. It has no use. And how do you know? It's from your process of what you're pre-processing. And that's why you see that I started for everybody. I started from pre-processing, taking in data. Pre-processing is so paramount, sir. You know, you get and pre-process your data very well. Your model will hardly have problem. So that's the area. All right. Then for image compression, can you see, and noise reduction? That's what they use in all this is this a technique? All these our what's it called? Headset.
Cancellation of voice cancellation or noise cancellation.
Sir. In fact, that's the algorithm that they use in creating those things. Sir. The chip in them, noise cancellation. Thank you very much, sir. That's what they've done, is SVD. It understands when I'm talking like this now, so that when I'm taking a class like this, I am the principal component. anything after my voice is noise.
Noise.
Do you get it, sir?
Yes, sir.
Everything after my voice that is talking to you now is classified as noise because somebody has trained the model to understand using what SVD technique. So that's just it. And that's what they write into the chip that they put into the headset.
Very interesting.
Yes, sir. And that's one thing with AI, and machine learning, it opens you to a lot of possibilities. We see things that are happening around us, you realize that, oh, this is what is working underneath it. This is what is just going on. So let's go on, sir.
Yes, sir.
So look at our SVD for our SVD Python implementation. We can use NumPy. We can try with a NumPy and say what? We have random number between 5 and 3. Then call what? USVT. You can just call any number. So now say what? Print the singular value of S. So want to know, does he understand the random number that was put in there? Then can he among U, S, and VT in this our program, in this our random number, can he pick only the value of S? Can you see what you are trying to do, sir?
Yes, sir.
You want to see just what value does S hold between random number of between 5 and 3. We can also call the singular value of U. So that's what your what's it does. That's what SVD does. Yeah. So you can see that we are using it in linear algorithm, SVD. So it's NumPy. You can see call SVD in NumPy. So we'll see how we use it also in our pipeline implementation. So these are things that help you, and people like, how did they do this? How did they do that? It's because somebody has sat down, somebody has taken the time to sit down to understand what is going on in the data set before creating a model for that data set. So look at the situation. Choosing when do you choose between this PCA, LDA, and SVD, like I've told us. When you want to use PC on labeled and high-dimensional data, you can see that PCA and SVD, you can use either PCA or SVD. Yes, sir. If you have classification with labels, it's only LDA. Exactly. Then when you have text or matrix factorization, or you have voice, you have sound and things, noise, is SVD. So you realize now that SVD can do the work of PCA.
Yes, sir.
Exactly. Then, and I said something here. When you have interpretability is needed, sir, avoid what? Dimensionality reduction. If you are going to do it, make sure that you have saved a copy. You have saved a copy of what? Of that data before you start reducing dimension. So that after reduction, you can do a comparison of the compressed data features and the original one.
Yes, sir.
So that's okay. Then we go to advanced feature selection method. Advanced feature selection method. Why are we doing that? We want to evaluate our reduced features. So we need those things. Commonly, we use the cumulative explained variance to decide how many components to retain. Yes, if we are doing that in traditionalism, which is a rule of thumb, it says we'll keep enough components to explain 90 to 95% of your total variance. Just like the way I will give it to you now to do your what's it called? Your medical analysis and insight. I send you. So this is just we are just doing evaluating it based on this is why these are the ones we can reduce using our own 90 to 95%. But sometimes it might not be enough. It might not do justice to what we want to do. Yes, it might not do justice, sir. Because as humans also we are prone to error. And based on the kind of model we want to build also, this might not do justice. So that's why we need we need these following tools or techniques. We have what you call the RFA, which is the recursive feature elimination. Yeah, I said it's a wrapper feature selection method that iteratively trains a model and removes the least important features until the optimal subset remains. Can you see, sir?
Yes, sir.
Recursive. It keeps on. It will be checking them. It will be running at a train, and what it will be removing what least important features until it is remained with like the subset. So like we have a three. You remember our subset now? Our set. We have three different values where they intersect together, where the three of them meet together. That makes them what a principal component. That's what recursive does. It will eliminate other features that cannot work that until it gets what the optimal what subset. And what does it do? It works by ranking features based on the model's importance scores and eliminating what the weakest features step by step. Yes, it doesn't just remove everything at once. No, it will train. When I trained, this feature did not do anything. It will remove it. It will do the training again. When we are training now, this guy performed less. It will remove it. Maybe like 15 features until maybe not gets and oh, if I get here and remove any other one, it will affect the model performance, then it will stop. So I say it helps reduce dimensionality, improves your model performance, and prevents overfitting. I tell you, if you try this recursive elimination into your model, sir, in fact, you will be rest assured that your model will perform very well. And even if it doesn't even give up to 90% diagnostic based on a clinical record, at least you'll be able to achieve between 82 to 85. Right. Which is still better than saying my model is 99%. Then I sent to Dr. Bello, then Dr. Bello said, this model did not perform more than 29%. You see that side, there's a problem.
Yes, sir.
Exactly. So RFE, recursive feature elimination, is good. Look at how it works. I said it starts with all features. It starts to train the model. It ranks feature by importance. Removes what? The least features. Repeats the processor until it has finalized what? The selected features. So you can see that it's a very, very good. Can you see recursive? Can you see what recursive?
Yes, sir.
I started to okay, this feature is not good, but we report the good feature. We'll come back again and start again. Like that. It keeps on going until it doesn't see what it does not see what it is looking for.
Sorry, I'm not able to make a phone call at this time, but you can.
So you can see that. What are the advantages? It uses what? A specific estimator. And what are those specific estimator? Your logistic regression and your random forest. There are still more of them. All these your linear and forest algorithms. It's so good that when you are training them, somebody was doing something. I wrote a paper and somebody told me, why did you waste your time first to first use ANOVA and mutual importance gain to first select features, then you now use the features. He said you'll have used RFE now. So I couldn't sleep that night. I felt very bad. So do you know the stress I had to do first? To first set up ANOVA, to first pick 7 best features, then mutual information gain, pick 7, then we'll now feed into the model. This one, all I need to do is just make sure that my data is well cleaned and just initialize RFE. It will do it for me. And at the end of the day, when it gives me my classification report, it will not tell you these are the features that I use in the classification report or diagnosis. So you can see that it is an informed learning that me going to go and be using ANOVA and all those things.
Yes, sir.
So those are the, sorry, please, let me just pick this call. I'm sorry.
All right.
I had to pick that call.
No
I'm back.
No problem, sir.
Yes, sir. Then can you see now that what? It said you can define the number of features to select. Can you see how good it is, sir?
Yes, sir.
Very good. Then it tells you it is suitable for what? Medium-sized data sets with moderately high dimension. Just like that one you are saying. You have a data set of about 500, sir, with 7 features. you know that your RFE is good, sir.
Yes, sir.
Very easy. You don't need to be stressing yourself. It does the work for you. All right. What is the application? You selecting all features for it. Exactly. I loved when I was reading, I saw this. Anytime you are doing a predictive model, I was so pained, so I didn't know. Don't go and be all this ANOVA, chi-square. So you're just stressing. You are stressing yourself. I didn't know I was stressing myself, sir. I felt bad. You see these people, the way people, when you learn this, as I tell people, don't shy away from learning. Anybody can teach you.
Yes, sir.
This is somebody that I taught in a class. Now call me, sir. He said, sir, I know you've done this, but I was just doing and I saw it. Sir, I couldn't sleep that night. I was like, oh my God, if I had just done this, I wouldn't have stressed myself. Can you see that it will improve what? Your interpretability in your regression. So instead of me trying to be using smooth analysis so that my interpretability will be okay and things, or GradCam, RFE, sir, has done it for you, sir. I don't need to be calling GradCam and all these things for interpretability. So you can see that not only does it work on model selection, it helps your model level performance and also improves what interpretability of what of your model. Oh, so it's a powerful what feature selection technique. Yes, look at the Boruta algorithm. This Boruta is majorly for what? Your random forest. So it's a wrapper method. When they say wrapper, because we are compressing, so they call it a wrapper, you know. When you compress it like sweet, you are wrapping your features inside like a sweet. So that's why we call it a wrapper method. So based on random forest, it compares real features with randomly shuffled, which it calls the shadow features, to determine the importance. That's just it. Only features that perform the shadow features are retained. Can you see, sir? So the shadow feature is what the original feature that it believes that should be the feature to carry out the work. So it will not look at, okay, let me not be like, I'm just being biased. This is the way we bias. Let me not test other features against these shadow features. So only the feature, if you can you see the word, as I put the word outperform, I think in the slide, I will go and put it in capital letter in bold so that you see. Only features that perform the shadow features are retained. Anyone that performs as the shadow feature will not be retained. If the shadow feature has performed at a level of 80% and it performs at 80%, it won't take it. But if it performs at 81, it will keep those features. Because it believes that those features will what their principal components that will help the model perform well. Can you see what it does? Can you see now? Can you see the original?
Yeah.
Can you see the shadow features? So it begins to pick them. Let's be testing them now. This is it. This is the random forest in it. It will now begin to pick from here. Maybe these are other features that have been, you can see that they have been concatenated. So it will now pick F1. If I raise F1 to shadow feature, does it meet up? If it doesn't meet up, it will discard. Any feature that does not meet up. So at the end of the day, you now see that you now produce what? Can you see that it has produced what? A concatenated what? Feature. So all he has done here is that this is the shadow feature, or from original data, these are the features that are passed. So he brings the two of them together, sir, and combines them. So if you have F1 to F8, it will only test them against this guy. Anyone that does not meet up with this criteria, yes, sir, they are thrown away. Is that clear, sir?
Very clear, sir.
All right, sir. What is the advantages of Boruta? It captures non-linear. So you can see that the first one is for linear relationships, sir.
Yes, sir.
Yes, sir. Your RFE is for linear relationship. When you talk of random forest, random forest is like a tree-based decision model.
Yes.
And when you're talking of tree-based decision model, you are talking of what? Non-linear data. Exactly. Relationships. So that's what it captures best. Then it is robust to noisy and high dimensional data sets. Very, very good. Then it provides all relevant features, not just what? A minimal subset. It will pick all the which ones are the relevant one. Any other ones, I will throw it away. Unlike the PCA, the RFE that starts training, oh yeah, this feature did not do very well, throw it away until it keeps. This one will look at them very well and pick all relevant ones and use it for what? For your classification or your clustering or your predictive. So what is the application? Its application is on complex data sets with correlated or what, or non-linear. So you saw that data set where we are having problem with the non-linear features. We just use Boruta, sir. Boruta will help us. Immediately our PCA, sorry, I said our PCA, our SVD and LD help us to know that, oh, they are not non-linear. Immediately, sir, you just come and apply Boruta. So you see what it says. You can use it to select important features for these models. Random forest, SGBoost, or what? Other tree-based. So I mentioned it from the beginning. It's for tree-based models where there's what? No linearity. No linearity. Yes, linear. The features are what? They are not linear. So if they are not linear, you cannot what? You don't bother about it. Just use a Boruta algorithm. Okay. Then you have what you call your SHAP, which I call the explainable feature importance. It's called your shapely additive what? Explanation. It was based on a game theory. It's a game theory-based model to interpret what? Models prediction. What does this one do? It calculates each feature's contribution to individual what? Prediction and overall model. That's what it does. Shapely will look at all your features. What contribution does it have on prediction? And it will analyze them, this one, so that when you are retraining next time, you will know that, wait, this feature is just a waste of time. Unlike the way RF will first be testing, dumping, or Boruta will try to, look at them, use the shadow to do this one. This one, we first do all the whole training. Before it does the whole training first, maybe you throw sharply on it. It tells you don't use color code. It will tell you, no, forget this side. Forget all these ones. They are not necessary at all. Concentrate on what? On this. Can you see? This, yes, this what like a sharp, can you say sharp value for age? So it's possible that I've given it that the ones that in red should be the ones that are, or the red ones are the ones that do not correlate or are not good for what? For model classification or model prediction. Is the blue one. So from this, you begin to know. But this is what a sharply looks like. It tells you which one are beyond. This is the, can you see this is the line? So we know that everything from below like this now are not useful. All the things we need, sir. You can see that it's forming like a bell shape. So what we need from here to here, they are doing very what? Doing very fine. So anything we use around this place above, we surely what? We surely work fine. Advantages. Can you see what I said, sir? Now, you see that these are the reasons why I love all these things. RFE works for linear models. Boruta works for what? Tree-based. These guys work on what? Any what? Machine learning model. Anyone, sir. So, sir, if you want to work now, which one will you use, sir?
Sharp.
Sharp. You see that it makes our life easier, sir. Why should I be cracking my head to say which model is linear, which model is not linear, sir? It makes any linear, any model, sir. Just carry out a sharp on it. For what? For feature selection. It saves you the stress. Then it provides both what? Both local and what? Global. Yes. It will explain each feature, sir. It will tell you what is the essence of the feature in that particular data set. Just like the way you are telling me that I cannot expunge age from some place, that just the way I cannot expunge ethnicity. Sharp will do everything for you, sir, and give you a summary table. Can you see? It produces a visualization to understand what? Feature impact. You will tell it when you are writing your code, say, or after you are done, give me a summary table to tell me which of these features correlates that can do what I need it to do. So maybe it draws the sharp graph or the sharp value. It generates a table for you that gives you what? Insight. So you don't need to stress yourself. What is the application? Explainable AI for what? Regulatory or what? Medical purpose. In fact, anybody who is doing a medical, what's it called? Diagnostic model and does not use Sharp or you use GradCam. But now that I know that Sharp, I was using GradCam before, now I've upgraded my PhD thesis and I've said what I will be using GradCam and Sharp. Why am I using GradCam and Sharp? So that we will not tell the superiority, okay, I use GradCam saw this, then what did Sharp see extra that GradCam did not see? So that's just then you can use it for what? It can be used for model debugging and feature interpretation. Yes, okay. You can see where problem, somebody comes and gives you, my model is not, I don't know, I've done all hyperparameter tuning. You just say, guy, don't bother yourself. Give me your data set, let's plot the Sharp value. So immediately you see some pattern in the data sets, your model cannot work very well, sir. Because you did not, so there are some features that you still added that you are supposed to have expunged. And you didn't expunge it. Then you can give a consultancy and say, sir, you pay me 50,000, I will help you extract the models that you, features that you need. And you do a graph, just do a 2-page documentation, and you collect your money in your pocket and you leave, sir. As simple as that. So that's why I was telling people, when somebody was telling me job opportunities in AI, I said there are lots of job opportunities, sir. Ordinary EDA is enough to fetch you a livelihood.
Yes, sir.
Let people know that you can check their data, tell them the features that are important. These are tools that are easily available. You are not paying for them, sir. Just know how to use them, and you are good to go. So let's go on, sir. So now I'm comparing like I always do. I just like doing that. I like doing that. Exactly. Just like the way ANOVA, Chi-Square, Mutual Information Gain, they are data independent. So for these models, feature selection method I've given you, they are model independent. RFE, all of them are model independent. Only RFE is what is non-linear. Sharp can work on both what? Non-linear and what? And linear. So Boruto can only work on only non-linear. RFE can only work on linear. Can you see that interpretability for RFE is very medium? If your data is more than a particular answer, it will mess up. I say what? Simple and model-based, very simple. Boruto is still okay. It can be robust and what? It can work on and non-linear. But Sharp is very high, sir. That's where your explainable AI comes in. You can do a lot of things. So it's just so wonderful. So wonderful. So I think this brings us to almost getting to the end of our. Okay. So I now talked about what is the difference between feature selection and dimensionality reduction. Because somebody was asking me, saying, what this one, that. I said, don't worry. It's simple. When you do feature selection, sir, you still keep your original features. All you are looking for what are subset of the features that what you want them to do, what that you want them to work for that model, so that the model can work as good as possible. But when we are talking about dimensionality reduction, we are creating new features now. Like I explained to you, from age, we can create age group. Are you still here, sir?
Yes, sir.
All right. Exactly. From age, you can create age group. So you can see that there are two different things. Feature selection keeps your original, but creates a subset from them. Maybe out of 20 here, it takes only 7 can work. It brings them out. This one we create new. And that's why we call it what? Transform components. It will match some features together and use it to form what? A new component. So best practices, like I still tell people, you must embrace best practices. You see what I tell you? I'm happy I wrote it. I didn't even put it. Always standardize before you do PCA and LDA. Funny enough, standardizations can solve your problem. That you might not need dimensionality, reduction or anything again. Then always do what I call cross-validation after feature selection. Yes, always employ cross-validation. It's always good. Then avoid removing too many features without testing their performance. Then anytime you are using your PCA and LDA, combine them with your RFE or SHARP for interpretability. It's always good. So I tell you, immediately you do this standardizer, it doesn't give, you don't have any problem. You don't need to call these guys. That's why you find out that not all models use PCA, especially when when standardization has solved the issue. If the standardization solve the issue, the next ones are not okay. But if standardization does not solve the issue, then these next 3 rules are very, very necessary. Very, very necessary. So what have we learned today? We've learned the course of dimensionality. We've spoken about principal component analysis, linear discriminant analysis. We've talked about the SVD principles. Yes. When and how to compress your data, then we've talked about what advanced feature selection techniques, which is your RFA, your Boruta, and what? Your Shapley discriminative explanation. So which is your explainable AI. So I don't know if there's any question for me.
I am just